Bonding a la Mulliken, Introduction to Molecular Orbital or MO Theory. We've recently taken a look at valence bond theory and valence shell electron pair repulsion theory. These are very powerful theories that have a lot of predictive power. They help us to predict the molecular geometry, whether or not a molecule is polar or nonpolar, and allows us to describe bonding in terms of atomic orbitals. However, valence bond theory and valence shell electron repulsion theory have some limitations. One limitation is that these two theories assume that all electrons pair up whenever bonding takes place. This doesn't account for a few molecules known to be stable, but may not have electrons that are all paired up. The first category of molecules are molecules with odd numbers of electrons. These molecules, however stable, cannot be described properly using these two theories. There are also molecules with even numbers of electrons that experiments show are paramagnetic. We've learned in previous chapters that paramagnetic atoms have unpaired electrons, which allow them to interact and be attracted to the poles of a magnet. One good example is oxygen. Our Lewis structures and valence bond theory descriptions of oxygen show that all electrons are paired up. However, if you take liquid oxygen and pour it through the poles of a magnet, the liquid oxygen will stick to the poles of the magnet. This indicates that there must be unpaired electrons in oxygen structure, something that a Lewis structure or valence bond theory cannot show. Valence bond theory and valence shell electron pair repulsion theory also does not give energy levels for molecules. You may have seen in your textbook some energy level diagrams that match up with hybridization schemes. However, these energy level diagrams are inaccurate. Experimental evidence shows that the atomic orbitals are not affected by such things as hybridization in molecules. Finally, valence bond theory and valence shell electron pair repulsion theory does not account for resonance for certain molecules. When we describe a molecule that does have resonance structures using valence bond theory, we have to keep the double bond static. Whenever a theory is limited, we either need to modify the theory or come up with another theory. In this case, there's another theory that we can use to describe bonding, and this is molecular orbital theory. Molecular orbital theory was formulated by Robert Mulliken in the 1930s. The goal of molecular orbital theory is to describe electron structure in molecules that is very similar to that of atoms. Recall that atoms have their electrons distributed through orbitals. We can write electron configurations to show where electrons are energetically. In molecular orbital theory, therefore, we would have to come up with molecular orbitals that describe where electrons are in molecules. As with atomic orbitals, this would require us to solve the Schrödinger equation for a molecule. This would give us the molecular orbitals and the energies of the orbitals. However, you might remember that we could not solve the Schrödinger equation for an atom with more than one electron exactly. The same thing happens when we try to solve the Schrödinger equation for a molecule. We can only solve the Schrödinger equation exactly for one electron molecules. For example, a hydrogen molecule with a positive 1 charge. However, just like with atomic orbitals and the electronic structure of atoms, we can approximately solve the Schrödinger equation to get molecular orbitals and their energies. This is what Molecular did. Molecular's theory from molecular orbital theory takes linear combinations of atomic orbitals to calculate molecular orbitals and determine their energies. We talked about linear combinations when we talked about hybridization. However, in molecular orbital theory, we take linear combinations of orbitals that are on different atomic centers. In hybridization, we take linear combinations of atomic orbitals that are in the same atomic center. Our molecular orbitals will therefore be distributed upon two or more nuclei. However, we will only discuss molecules with two atoms. We call these diatomic molecules. Before we talk about how molecular orbitals are constructed, we should take a look at the same exercise with sine waves to describe two phenomena, constructive and destructive interference. If we take two sine waves that are in phase and add them together, they will both add together positively to give constructive interference. Notice that the new wave, which was the linear combination of the first two waves, has an amplitude that's twice as high as the original two waves. This is because each wave constructively interfered with one another. We can do the opposite and add two waves that are out of phase. The out of phase waves will cancel one another out, and we get what's called destructive interference, a wave with no amplitude. Therefore, we've effectively destroyed the wave. Remember that atomic orbitals are three-dimensional waves. And since they are, in fact, waves, the same thing can occur when we add together atomic orbitals to form molecular orbitals. This gives us two types of molecular orbitals. The first type of molecular orbital is what we call a bonding orbital. Like with the constructive interference of sine waves, we can add two atomic orbitals together in phase to create what's called a bonding orbital. If I take two 1s orbitals with the same phase, here represented by being the same color, I will get one molecular orbital that is twice as big as the original atomic orbitals. Notice that the molecular orbital puts electron density around two nuclei, but more importantly, in between the nuclei, representing electron sharing. This is our constructive interference. In terms of energy, bonding orbitals tend to be lower in energy than the original atomic orbitals. This means that they will stabilize the molecule. Here's an energy level diagram that shows the energy of the two 1s orbitals. If they come from the same atom, they will have the same energy. Here's the energy of our bonding molecular orbital, which is lower in energy than the atomic orbitals that made it. Why is the energy lower when you make a bonding molecular orbital? The reason why this orbital is so stable is basically because it allows the electrons more space. Therefore, you've delocalized the molecules over two atomic centers. The plot on the right shows the potential energy of the electrons versus the distance between the two nuclei. The solid curve shows the experimental orbital energies. Notice that the energy reaches a minimum when the nuclei are a certain distance from one another. This distance would be the bond distance of a hydrogen molecule. This shows that the energy is lowered when electrons are allowed to be between two nuclei. You can also get what's called an antibonding orbital. This results from adding atomic orbitals out of phase. We show this by having two 1s orbitals with different colors. These two atomic orbitals will form what's called an antibonding orbital. Notice that if you look between the two nuclei, which are represented by the small black dots, there is no electron density between the nuclei. This represents our destructive interference. The electron density between the nuclei has canceled itself out. If we take a look energetically at our antibonding orbitals, they tend to be higher in energy than the original energies of the atomic orbitals, and higher in energy than the bonding molecular orbital. This is because this orbital does not promote electron sharing. We label our molecular orbitals using the sigma and pi symmetry labels that we used in valence bond theory. Sigma symmetry means that the orbital is cylindrically symmetric around the bonding axis. Pi symmetry says that there is electron density above and below the atomic axis. We distinguish bonding orbitals from antibonding orbitals using an asterisk. It is also common to put in a subscript the type of orbital that the molecular orbital was formed from. In this case, we formed our sigma molecular orbitals, one bonding and one antibonding, from 1s orbitals. In Chapter 8, we took a look at orbital occupation diagrams for atoms, where we showed explicitly how the electron spins are placed in each orbital. We can do the same thing with molecular orbitals. On the right-hand side of the screen is our completed molecular orbital diagram for row 1 elements. We could use this molecular orbital diagram to describe any molecule formed between two hydrogen atoms or two helium atoms. Our molecular orbital diagram usually shows the energies of our atomic orbitals on the left-hand and right-hand sides. In the middle are the molecular orbitals, labeled appropriately. We place electrons in our molecular orbital diagram by following the same rules we follow for writing orbital occupation diagrams for atoms. We follow the Aufbau principle by putting the electrons in the lowest energy molecular orbital first. We follow the Pauli principle by making sure there's no more than two electrons in the same orbital, and the two electrons, represented by arrows, must have opposite spins. We can also follow Hund's rule by placing a single electron in orbitals with the same energy before pairing them up. In the case of the hydrogen cation, which has one valence electron, that one valence electron goes in the lowest energy molecular orbital. That would be the sigma 1s orbital. We can also use these diagrams to calculate the bond order for a molecule. We learned about bond order in Chapter 9, which tells us the number of shared electrons in a Lewis structure. Calculating bond order in molecular orbital diagrams allows us to create a correspondence between our Lewis structures and our molecular orbital descriptions. However, in molecular orbital diagrams, talking about a number of shared electrons is very artificial. From molecular orbital diagrams, we can calculate the bond order by taking the number of electrons in bonding orbitals and subtracting off the number of electrons in antibonding orbitals, then dividing this difference by 2. For our hydrogen cation, the bond order would be 1/2. There is one bonding electron and no antibonding electrons. We would divide the number 1 by 2 to get 1/2. In molecular orbital theory, if you calculate a non-zero bond order, this means that a stable bond can form between the atoms. Although we can't draw a valid Lewis structure for the hydrogen cation, we know that since its bond order is not equal to 0, that it can exist stably, and in fact it does in the gas phase. If you calculate a bond order of 0, this means that you have the same number of bonding electrons as antibonding electrons. This results in no stable bond forming between the atoms. Bond order can help us predict a few other things. First of all, it is possible to have bond orders that are half-integer values, just like for our hydrogen cation. This typically occurs when you have an odd number of electrons in the molecule. This is perfectly valid. Molecular orbital theory just tells us that if a bond order is not equal to 0, a stable bond will form between the atoms. We can also use bond order to predict what happens when electrons are added or removed from a molecule. If we increase the bond order or decrease it, we can change bond energy and bond length. As the bond order of a molecule increases, the bond energy also increases. We know this because a single bond, which has a bond order of 1, is weaker than a triple bond, which has a bond order of 3. Also, if we increase bond order, the length of the bond decreases. We also know that single bonds are longer than triple bonds. Let's look at some examples of describing molecules with molecular orbital theory. We're going to take a look at orbital occupation diagrams for the hydrogen molecule and the helium molecule and calculate their bond orders. We will compare the bond order of hydrogen to its Lewis structure and use the bond order of helium to relate to what we know about the reactivity of noble gases, even with themselves. For our hydrogen molecule, we first need to know the number of valence electrons. The hydrogen atom has 1 valence electron, so hydrogen molecule will have a total of 2 valence electrons. Here's our molecular orbital diagram for row 1 atoms. Our 2 valence electrons will be paired up in the bonding 1s molecular orbital. Here we are following both the Pauli exclusion principle by pairing up our electrons and the Aufbau principle by putting them in the lowest energy molecular orbitals, which are found in the middle of the diagram. If we calculate a bond order for hydrogen, we need to take the number of bonding electrons, which is 2 in this case, and subtract from it the number of antibonding electrons, which is 0. This gives us a bond order of. If we look at our Lewis structure for hydrogen, we see that there is one line in between the hydrogen atoms, which represents a sharing of 1 electron pair. This corresponds very well to our bond order that we calculate from molecular orbital theory, which means that both theories can be used equally to describe the bonding in the hydrogen molecule. Next, we take a look at helium. If we look at a helium-2 molecule, each helium atom would have 2 valence electrons for a total of 4 valence electrons. We can use the same molecular orbital diagram to fill in the electrons for helium-2. Here, we put 2 electrons paired up in a sigma 1s bonding orbital and 2 electrons paired up in a sigma 1s antibonding orbital. Remember, your electrons should really only go into the center energy levels, which are for your molecular orbitals. We can use this diagram to calculate a bond order for helium. Helium-2. This time, we have 2 bonding electrons and 2 antibonding electrons. This gives us a total bond order of 0. This predicts that if we took 2 helium atoms and tried to make a molecule, that no stable bond will form between them. We know that helium is a noble gas, and noble gases are typically unreactive towards other elements and with each other. Helium gas actually exists as individual helium atoms, not molecules like in the case of hydrogen. Therefore, our molecular orbital description of helium-2 corresponds to the behavior that we know about helium.